Hi, it's Dr. Hansen again, and now I want to look at acids and bases. The good news is that this is something that you've worked through in freshman chemistry, and then you worked through it again in organic chemistry, and you probably have done problems related to this in biology. And so you all have studied to some extent what pH means, what a pKa is, how weak acids and weak bases can be buffers, and most of you have at least heard of the Henderson-Hasselbalch equation, although you probably don't like it. I'm not here to teach a lot of freshman or organic chemistry. I'm here to zoom in on what really matters. And pH does matter, pKa matters, and even the Henderson-Hasselbalch equation is going to be used, so you do want to have a working knowledge of pH. And because there's some algebra here and a little bit of understanding of logarithms and exponents, this is the one part I think that a lot of people have the most trouble with. Certainly I expect about a third of you to say, hey, I know all this stuff, no big deal. In that case, you'll be able to work through it quite quickly, won't take too much of your time. But I also believe that quite a few of you will struggle in this. And so again, I want to remind you, I am available to help. I want you to phone me. I want you to email me. I don't want you struggling for hours agonizing over this. I believe that 90% of what I say you're going to understand, but different people will get stuck on different parts. It's that 10% of the material that you're going to spend 90% of your time on. That's why it's so important to seek help. It isn't just that you're going to save a lot of time and get through it more quickly. It's also that you'll have a deeper and more complete understanding of it. And I think if you call me, you'll say, oh, is that all there is to this? A lot of these are very simple concepts that if you get it, then the whole picture makes sense. What does pH mean? If you have a solution at a pH of 7, what is the proton concentration in terms of molarity? Please pause the video and answer. I'm sure some of you are saying, sorry, Dr. Hansen, this is too simple. I'm also certain that others of you will be thinking, wow, I haven't even thought about pH in its fundamental definition since I was a freshman. That is a fundamental purpose in this preview video, to remind you of these very basic concepts, which really you should absolutely know cold. And I want to be sure there's no fuzziness in your mind at all. The simplest thing to say is, if the pH is 7, you simply take the value 7 and make it the negative exponent of 10. That is, the proton concentration at a pH of 7 is 10 to the negative 7 molar. And it really has to do with what the basic definition of pH is, and it's simply a way of avoiding writing 0.0000001 molar. That is 1, 2, 3, 4, 5, 6, 7 decimal places to the right of the decimal point. Another requirement is that you be familiar with the metric system. You need to know how molarity compares to millimolar, compares to micromolar, and compares to nanomolar. I will be using the word nanomolar quite a bit. Just to be painfully clear on that, 1 molar would be 10 to the 0 molar. 1 millimolar is 10 to the negative 3, or 0.001 of 1 divided by 1,000. 1 micromolar is 1 divided by a million, and 1 nanomolar is 1 divided by a billion. Of course, the formal definition of pH is that it is equal to the negative log of the proton concentration. That is equivalent to saying you can take the pH value, say 7, and use it as a negative exponent of 10, because logarithms and exponents are inverse functions. And in fact, will you use a little bit of math to formally solve for what the proton concentration is if the pH is 7? Take a little stab at that. It's going to help you, I think, when we get to Henderson-Hasselbalch in terms of thinking about how these values work. But I'm going to move on. As I've already mentioned, logarithms and exponents are inverse functions. So we've just said that the pH of 7 is the negative log of the proton concentration. So we multiply both sides of the equation by -1 to get -7 is equal to the log of the proton concentration. Then we use each side of the equation as an exponent of 10. We're doing the same things to both sides. If -7 equals log of protons, then 10 to the -7 equals 10 to the log of the proton concentration. And of course, the exponential of 10 can also be called the anti-log or inverse log. You can call it either way. So 10 to the log proton or the anti-log of the log of protons is simply the proton concentration. Therefore, 10 to the -7 equals the proton concentration. A little bit of maybe trivial arithmetic there, but I think it will help you some. When I solved this problem, why did I have to multiply both sides by -1 before I took the anti-log? This is a glitch for some people. Well, what would happen if I didn't multiply both sides by -1 to begin with? In that case, I would say we have 7 equals the negative log of the proton concentration. We don't multiply by -1. We take the anti-log, we get of both sides, we get 10 to the 7 equals 10 to the negative log of the protons. Now let's look at this. The anti-log of the negative log of the proton concentration doesn't equal the proton concentration. You're not taking the inverse function of a function. You're taking the inverse function of the negative value of the function. That is, the anti-log of the log of x equals x. But the anti-log of negative log x does not equal x, and I don't know what it would be. You're just going down a wrong trail there. So the point is that at the step that you take the anti-log of both sides of the equation, you need to be sure that one side is a logarithm, and that's all it is. The entire side is within the log function. Then when you do the anti-log, you get 10 to the -7, and we're down to the proton concentration. One thing that I notice every year is a number of students get test questions wrong on pH because they do the obvious thing. In your mind, you think, oh, if the proton concentration goes up, that means the pH goes up. We tend to think in terms of correlations rather than inverse correlations. So just be sure you remember the pH and the proton concentration are inversely related because it's the negative log. That means if the proton concentration increases, the pH decreases. If the proton concentration decreases, the pH increases. People just do that flip in their minds sometimes. It's something to keep in mind. We've already said what the proton concentration is at a pH of 7. In your mind, will you do a pH of 5 and a pH of 0? Just a very quick review, and then we'll move on. I like you to be able to think in terms of whole unit logarithms and exponents, but as we mentioned, the pH of blood is 7.4, which means the proton concentration is 10 to the -7.4 molar. And that's a little awkward to use. On a test, I don't want you to grab a calculator and hit buttons without understanding them. But right now, can you pause the video and tell me what type of metric units you would use to approximate that? Would this be some type of nanomolar, micromolar, millimolar? 10 to the -7.4. What's it between? Take a stab at that. Well, certainly 10 to the -7.4 is between 10 to the -8 and 10 to the -7. Please put in the greater than or less than signs. And again, the bigger the negative exponent, the smaller the number, so that 10 to the -7.4 is larger than 10 to the -8 and smaller than 10 to the -7. And that puts it between 10 to the -9 and 10 to the -6. What are the units 10 to the -9 molar, 10 to the -6 molar? Please pause and answer. You have to have some familiarity with these units. Little practice here. Well, 10 to the -9 is basically divided by a billion, which makes it nano. And 10 to the negative 6 is divided by a million, which makes it micro. So we have 1 nanomolar at 10 to the negative 9, 10 nanomolar at 10 to the negative 8, 100 nanomolar at 10 to the negative 7, and we can see that 10 to the negative 7.4 is between 10 nanomolar and 100 nanomolar. Now it turns out that 10 to the negative 7.4 molar is near 40 nanomolar. And really, if I wanted to get that answer, I would plug it into a calculator, but we're not going to bother to do that. You don't need to know how to deal with these fractional exponents, but you do need to know how to work with whole number exponents because our entire numbering system is base 10, and these logarithm and exponents are all base 10. So you should be able to know that 10 to the negative 9 means 1 divided by 10 to the 9, which is an extremely small number. You should know that's 1 divided by a billion. You should know that if we're talking molarity, 1 divided by a billion molar means 1 nanomolar. 10 to the negative 6, 1 over 10 to the 6, that is 1 divided by a million. 10 to the negative 9 is a much smaller number than 10 to the negative 6. And you should be able to go from 1 nanomolar to 10 nanomolar to 100 nanomolar and realize that 10 to the negative 7.4 is between them. The ability to work with metric and with base 10 logarithms and exponents. And of course, if we're looking at pH values that might have some meaning, black coffee and beer are pretty important, slightly acidic, seawater, slightly basic, blood, barely basic, pH of 7.4, 40 nanomolar of protons. And of course, you might be using a 1 molar strong acid or 1 molar strong base solution that would have a pH of 0 or of 14. And as we've been saying, the pH will be the negative exponent, or it can be written out much longer. Very simple to go between basically numbers and exponentials. This particular slide is meant to show graphically how pH compares to the proton concentration. As the pH goes higher and higher and higher, that means the proton molarity will get smaller and smaller and smaller, so that all the proton concentrations are very tight against the line here, 10 to the negative 14, 10, 8, 6, 4, 2, 1. It's only when you get down near a pH of 1 that you begin to see a separation. So at a pH of 0, any exponent to the power of 0 is exactly 1. That's where you cross the axes. And for that matter, you could have a pH of negative 1, in which case that would be 10 to the negative negative 1, or 10 to the 1 molar, or 10 molar. It's a very frequently shown graph to try to give insight into that exponential relationship. But let's look at buffering, and I'm going to begin by looking at a strong acid. Let's say that we have a concentrated solution of hydrochloric acid, and we dump it into a liter of water, and we add a total of 100 millimoles of hydrochloric acid. What will the proton concentration be, and what will the pH be? Will you calculate that quickly? These are the most basic understandings you'll need. Hydrochloric acid is a strong acid, which means the proton and the chloride completely dissociate. But before we solve the problem, a quick question. Why is hydrochloric acid such a strong acid? Why does the proton so readily come off and leave behind a negatively charged chlorine? Please pause and answer right now. If you had some trouble with that, I'll tell you a clue. It has something to do with electronegativity. Another clue, where is chloride on the periodic table? Why would chloride be so able to stabilize a negative charge? So if you add 100 millimoles of HCl, you've added 100 millimoles of protons. That means in 1 liter there's 100 millimoles, which makes the concentration 100 millimolar in protons. What does that make the pH? Of course, pH is defined as the negative log of the proton concentration in molarity, not in millimolarity. So we have to look at what this is in molarity, which is 0.1, and we will take the negative log of 0.1. Please try to come up with that quickly. and I'll move on. The logarithm of 0.1 is -1, so the negative logarithm of 0.1 is 1. Now, I don't expect you to instantly be able to pull that out of your head, but just let me remind you, what's the logarithm of 100? Well, 10 squared is 100, so logarithm of 100 is 2. What's the logarithm of 10? 10 to the 1 is 10, so logarithm of 10 is 1. Logarithm of 1 is 0, because 10 to the 0 is 1. Anything to the power of 0 is 1. And the logarithm of 0.1, or of 1/10, is -1. In order to check whether or not the logarithm of 0.1 is 1, you absolutely need to understand that the anti-log function or the inverse log function is the exponential function. So we can say, does 1 equal the negative log of 0.1? We simply take the anti-log, or we use both sides of this equation as an exponent for 10. So 10 to the -1 molar is equal 10 to the base 10 log of 0.1. 10 to the log cancels. They do the inverse of each other, leaving you with 0.1 molar. So, in fact, that is the correct answer. Really good to have some feel for exponents in logarithms. But what if we're not dumping that strong acid into water, but instead, let's say we inject it into some blood? Let's say we take a dog and we inject 150 millimolars of hydrochloric acid into his veins. And by the way, this was a real experiment, before all that government regulation. I think it was the 20s or 30s. But there was this guy, Robert Pitts, who did exactly that, and he noticed that it changed the pH. Is this what you would predict? If you're adding hydrochloric acid, would that cause the pH to go down? Please answer. A low pH means high protons. High pH means low protons. So the pH is inversely related to the proton concentration. And it's so easy to think, high pH, that must be high protons. But it's not. It's the complete opposite, because it's a negative log. So the point is the pH changed, but I would have predicted a bigger change. This is a lot of hydrochloric acid to add. Why was the dog still alive? Can you answer the question? What happened to those protons? Buffers. Our blood has a lot of buffers, such as carbonic acid. And we also have protein in our blood, like hemoglobin, with histidine side chains that at fairly near physiological pH can accept or give up protons. And there's inorganic phosphate, which can give up or take protons. So now we've added the hydrochloric acid. The pH didn't change as much as we would have predicted. What happened to the protons? How does a buffer work? Please pause and answer and tell me where those protons went. Well, this is what's so neat about a buffer. If we have a millionfold carbonic acid over proton in the blood, that means that when you dump the protons in, they can stick to bicarbonate, the conjugate base, and convert it to carbonic acid. So this is Le Chatelier principle. You're adding hydrochloric acid. Some of the protons stick to bicarbonate to make carbonic acid. Some still float around to lower the pH. Some of them stick to histidine. Some of them stick to inorganic phosphate. And what's really neat about your blood is those proteins that need to work at a specific pH. If you have too many protons, their activity will be altered. But if you have too much carbonic acid or too much protonated inorganic phosphate, that has no effect on these proteins. So essentially, buffers remove the protons by slightly perturbing the equilibrium between conjugate acids and conjugate bases of buffers. Now, what if instead of adding hydrochloric acid, we add sodium hydroxide, a strong base that completely dissociates? We would predict the pH in the blood will go up because you're taking away protons. The proton concentration is going down, the pH goes up. But it won't go up as much as it would go up if you simply added those hydroxide ions to a bottle of water. Why? Because in this case, these hydroxide ions will grab the protons off of the acids and slightly perturb the conjugate acid conjugate base equilibrium. And again, it's very slight. There's so much buffer in your blood and usually so few protons exchanging. I'm hoping this very simple review of freshman chemistry helped you think about mathematically what pH means and how buffers work. If there's any ambiguity in your understanding of logarithms and exponents, of pH, please come and talk to me. I look forward to talking with you, and now I hope you'll go on and learn a little bit about the Henderson-Hasselbalch equation, which in fact I hope you don't even rely on. Rather, please listen to my simplified description of how Henderson-Hasselbalch works and how you can avoid having to do a bunch of algebra.